In this video, I'm going to show you why the measure of an inscribed angle is equal to 1/2 the measure of its intercepted arc. So as you can see, I have a circle here, this blue circle, and then I have an inscribed angle, the pink angle here. Okay? So here is your intercepted arc. Okay, and then this, of course, is your inscribed angle. Okay, right here. All right. So I'm actually going to undo the marking of the angle there now that you see it, but I'll leave that arc there for you to see. Okay, so we want to know, why is this measure down here 1/2 this? Okay, so let's think about it. What do we know about an intercepted arc? We know that it equals the measure of its central angle. Okay, so let's say I showed that central angle. So let me show that central angle right here by drawing a radius to here. One end of the arc. Good. And then drawing another radius over here. Perfect. So here, right here, oopsie, meant to have that be freehand. Okay, right here is your central angle, and whatever this measure is, that's going to be the measure of the arc. Now, if we can prove that this angle right here is twice the measure of this angle right here, we're in business and we're done, because then that means the arc will have twice the measure as the inscribed angle, or another way to think about it is the inscribed angle is half the measure of its intercepted arc. Okay, so I'm just going to delete those two markings, okay, so that we can work with some stuff here. All right, so I know this kind of looks complicated, but what if I drew in another radius? Whoops, I don't actually want to draw it freehand, I decided. I want to draw it perfectly straight. So I'm going to draw in a radius, okay, just like this. All right, now that did not bisect that inscribed angle, okay, but because it's a radius and this is a radius, look at this, we created two isosceles triangles. So this triangle here and this triangle here, okay. Now, what do we know about isosceles triangles? What do we know about them? We know that the base angles, so this angle here and this angle here, are going to have the same measure. Likewise, for the other isosceles triangle, this angle here and this angle here are going to have the same measure. So let's mark those off as maybe x, x, and y, y. Okay, so maybe I can switch colors here. Why don't we do it in, I don't know, purple maybe. That sounds good. Okay, so I will call this x. Okay, that angle right there is x. And this angle obviously has a measure of x as well. And then we'll call this one y and this one y. Okay, that actually looks like a pretty bad y. Let me redo that. It's hard sometimes to write so small, that's not much better, but you get the point. Okay. So now you might be saying, well, how are these measures going to help me figure out that measure? Okay. Well, what if I did this? What if I took, or what if I drew a diameter? Okay. So I want you to watch this. I'm going to draw a diameter from the inscribed angle to the other side. So as you can see, it's got to go through the center of the circle. It's going to be a diameter. Okay. So watch this. Okay, look at this. Now I know that you might not see it yet, okay, but take a look at this. I have, and I'll do it in black here so you can see, I have an angle right here that I've now created, which is part of the central angle, and I have another angle right here that I've created that's the other part of the central angle. So the black angle plus the red angle is going to equal the total measure of the central angle. Well, can I figure out what the measure of the black angle is here? And the answer is I can. Okay? Remember, this is right here, this angle right here, the black angle, and this angle right there, okay, sum to 180. They're supplementary. Okay, they're a linear pair. And this black angle is the exterior angle to this triangle that I have right here. So how do you find the measure of an exterior angle? Well, you know that it's just the sum of the two remote interior angles. So we know that this angle plus this angle is going to equal this black angle out here. So it's x plus x, so that is 2x. Okay, so we know that the black angle right here is going to be 2x. And you might be seeing where this is going. Look at this triangle over here. Again, the red angle is the exterior angle to this triangle right here, if I were to show you. Okay, this triangle right here, okay, that is the exterior angle, okay? So that angle, that red angle, and then I'll draw a double here so you can see, plus this angle inside the triangle are going to sum to 180. So then we know, since that's the exterior angle, that it's going to equal the sum of the two remote interior angles, which are y and y. So it's just going to equal 2y, because y plus y is 2y. Now, this is starting to get good. And you may see it, and if you don't see it yet, that's okay. All right, so take a look. Here is my inscribed angle. I know I'm coming out far, but this is my inscribed angle, okay? This is my central angle, okay? Look at the measures. The inscribed angle is x plus y, right? Because it's this angle here, x, plus this angle here, y. Okay, x plus y is the measure of the inscribed angle. The measure of the central angle, okay, is 2x plus 2y. Okay, so this is the inscribed angle. Inscribed angle, and this is the central angle. Okay, so look at that. So x plus y, and then I could factor a 2 out of here, and I get 2x plus y. So it looks like the inscribed angle is 1/2 the measure of the central angle, which makes sense. It's twice as big. So let's hypothetically say that the inscribed angle were 50. Okay, then that means this is going to be 2 times 50. Okay, because as you can see, x plus y, and if I told you it was 50, this is going to be 2 times 50. So look at that. It's double, just like we said. So therefore, since the measure of the arc is equal to the measure of the central angle, the arc is going to be 100. Okay, the central angle is going to be 100. And since the measure of the central angle is twice the measure of the inscribed angle, okay, we know that this must be 50. Okay, so there's your proof right there. Okay, you just kind of use that exterior angle theorem where the sum of the two remote interior angles equals the measure of the exterior angle, okay, and you end up with 2y, 2x, and then it's x and y for your inscribed angle. That's pretty cool. There are 3 possibilities though. Remember, we talked about this was the case where the center of the circle was in the interior of the inscribed angle, then there's the one where it's in the exterior, and then there's the one where it's actually on the side. So we're going to prove all 3, so that's the first one. Okay, good job. Here's another inscribed angle, and in this inscribed angle, the center of the circle is on the exterior. Oops, I didn't mean to make that point right there. The center of the circle right here is on the exterior of the inscribed angle. So in the previous one, it was in the interior. So now we want to try to prove that the measure of an inscribed angle is equal to half the measure of its intercepted arc. And how we did that last time, remember, was we said, well, if we can prove that the measure of the central angle is twice the measure of the inscribed angle, then that means that the measure of the inscribed angle is half the measure of the central angle, which means it's half the measure of its intercepted arc. So let's think about that. If we're comparing it to the central angle, what might make the most sense is to draw the central angle, right? So we can see what we're dealing with. So I will go from the center to here. Okay. So here is this right here is the central angle for this arc. Okay. So remember, the measure of the central angle equals the measure of the intercepted arc, so we just need to prove that this angle right here, okay, is twice the measure of this angle right here. Okay, so I'm going to remove those so that we have more room to work with. All right, so then how should we go about doing this? Well, if you recall in the previous proof, I ended up finding some isosceles triangles. And that's what's great about circles is if we draw a radius, and then we can draw another radius, and we can create an isosceles triangle. So I don't see any isosceles triangles right now, but what if I went from the center right here, oops, I don't want to use that, I want to use the, yes, more precise pen here, and I came out to here. Do you agree that I've created an isosceles triangle? Because here's one radius, here's the other radius, okay? So look, I will outline the isosceles triangle in pink so you can see it. Boom. Boom. Okay, so that pink triangle right there is your first isosceles triangle. So because it's isosceles, these two have the same measures. And then what do we know about the base angles? We know that the base angles have the same measure. So that means that this angle right here and this angle right here are going to have the same measure. So what do we want to call those angles? Do you want to call them y, let's say? We'll just call it y. Okay. Y and Y. Okay. So again, let's do a reminder, and I'll put it in red because red's a real bright color. This is the angle that we're looking for. Okay. This right here is the angle that we're looking for. Okay. So then if you notice, I have another isosceles triangle, and I will put it in, let's see, maybe like a lighter blue here. Okay, so I'm going to outline the second isosceles triangle that we have in lighter blue. Okay, so again, a radius, then we have a chord, boom, and then we have another radius. Okay, so here's our other isosceles triangle. Okay, so that has the same measure as that. Okay, I'll just delete that so you don't get confused here. So now that means that the base angles, so this angle here and this angle here, are going to have the same measure. So let's call those angles x. So here's an x here, and here's an x here. Okay, so this is just a reminder. We're looking for the red angle. We need to find the red angle, and we need to see how that compares to this angle. So let me do it in maybe a green. So again, it's hard to see, I know, but this was our inscribed angle. Okay, so I'm going to draw the inscribed angle in green. I know we're using a lot of colors here, but this was the original inscribed angle, and I know because I've outlined some triangles that we might have lost it. So I'm going to make the inscribed angle in green so we can clearly see it, okay? So this green angle, we're comparing it to this red angle, which is the central angle. All right, so now remember what had happened, and that was that I had drawn a diameter. So let's draw that diameter back in, okay? Because when we draw this diameter, we end up creating the exterior angles for these triangles. Okay, and that's the whole reason we do this. We want to create those exterior angles so we can use that exterior angle theorem. Boom. So now, if you look, this right here is the exterior angle to that pink triangle. Okay, that pink triangle, which is now green, pink, and gray. Okay, that's the exterior angle. So we know that the exterior angle is going to equal the sum of the remote interior angles. So it's y and y, the two pink angles, because it was the pink triangle, y and y. So that means that this big angle here that I just drew is going to be 2y. Okay? And then the other triangle, remember it was the blue triangle. Okay, so again, look, it's now gray, green, and blue. But we know that the angles are the x and the x. And this, let me see here. What's another good color? Maybe like a brown. This right here, okay, is going to be the exterior angle for that blue triangle, which has the base angles of x and x, okay, right here. So if you want to see again, the blue triangle, there's 1, there's 2, and there's 3. Okay, that was the blue triangle. Okay, I'm going to delete that just so that we can see better what I'm talking about. Okay, so this right here, because it's x and x, well, that must be 2x then. That means that this exterior angle here is 2x. So I'm just going to write the 2x out here and just draw a line. Boom. So that angle measures 2x, okay? So if we need this red angle right here, okay, well, the red angle, I'll go into red. It might be hard to read, but the red angle is just going to be, well, I'll use the colors that they are. So 2y, okay, minus, and then the 2x. Okay, and that's because 2y is the big one, minus this piece is going to give us this red piece right here. Okay, so then I'll write equals central angle. Okay, perfect. So we now know that the measure of the central angle is 2y minus 2x. Okay, so now the question was, what is the measure of the inscribed angle? So the inscribed angle, remember, is over here, so it's in green. Okay, so you see this green right here. I'll just refresh your memory. Okay, oops, I used a different color green. That's fine though. Okay, so that's going to be the inscribed angle. Okay, so let's see what it is. Well, look, we have a y and an x again. So as you can see, y minus x is going to leave you with the green one. Okay, so let's see. Y minus x, okay, and that equals the inscribed angle. So now look at this. We've got the central angle being 2y minus 2x and the inscribed angle being y minus x. So I'm going to switch to black here because I think that's one of the easiest ones to read. So we've got 2y minus 2x, and we're comparing it to just y minus x. And we can rewrite 2y minus 2x. We can factor out a 2 and just write it as 2 times y minus x. Boom. So then when we compare these two, we have, well, the inscribed angle, which is this one, versus the central angle, which is this one, okay? This is twice as big, see? 2 times y minus x versus y minus x, okay? So that means that the inscribed angle is going to be 1/2 the measure of the central angle. And that is our proof right there. So we proved that the central angle is twice the measure of the inscribed angle, which means that the inscribed angle is 1/2 the measure of the central angle. And the central angle is the measure of the intercepted arc, so therefore the inscribed angle is 1/2 the measure of its intercepted arc. Here is our final proof, where the center of the circle now is on the inscribed angle. So here are the two sides of the inscribed angle, and as you can see, the center of the circle is right here. Okay, so again, we want to prove that the measure of the central angle is twice the measure of the inscribed angle, because that will mean that the intercepted arc is twice the measure of the inscribed angle, and that means that the inscribed angle is 1/2 the measure of the intercepted arc. Okay, of its intercepted arc. Okay, so what might be good too is pause this video and try and attempt this yourself, because that's where the real learning occurs, you know, when you try something for yourself, not when you just kind of watch me do it. So I would recommend pausing the video, give it a shot yourself, give yourself 10-15 minutes, you know, and then press play and see how you did. Okay, so again, you notice that creating those, drawing the radius in, or a radius in, or radii in, was very helpful to us because we use that exterior angle theorem. So what we should do here is we should just draw in the central angle first, because that's really what we're comparing the inscribed angle to. Oops, I always do that. I want it to be a perfect line. Okay, so I'm going to draw in the central angle. So here is, so remember the black angle here is the inscribed angle, and then the central angle, I'm going to draw it over here, is pink, okay? So we want to compare this angle to this angle, okay? So again, because I have, you can see the triangle here, because two sides of the triangle, here's one radius, here's the other radius. Because of that, we know it's an isosceles triangle, so we know that this angle and the inscribed angle have the same measure. So let's call that x, and we'll call this x, okay? And as you might be able to see right now, this one was super easy. The central angle is our exterior angle. We don't even have to go through drawing that extra diameter or anything like that. We know that the pink angle right here is just going to be the sum of the remote interior angles, and that's going to be x and x. So the pink angle is actually simply 2x. And it's that easy. It's that simple. So right here you see, well, here's my inscribed angle, okay? And that measures x, and here's my central angle, which would be the measure of the intercepted arc, which is 2x. So clearly, the inscribed angle is 1/2 the measure of the central angle, or 1/2 the measure of its intercepted arc.